The presenter is the Sirshendu Das from the Indian Statistical Institute. Okay, you are ready? Okay, let's start.
Thank you for the introduction. So, hi everyone, I am Sirshendu Das, and today I will present our work on modeling and verification of sigma delta neural networks using Satisfiability Modulo Theory. Okay. So, in modern times, AI has transformed the world around us via multiple breakthroughs through diverse domains like computer vision, natural language processing, and reinforcement learning. And today we have like multiple different types of neural networks for specific domains. Like we have CNNs for the image processing and transformers for the NLP domain. So in summary, there are some requirements in real world requirements, and from that requirements we get some input output pairs and we feed it to the machine learning algorithm, and that gives you some artifact. So the challenge here is how can we verify these systems, because the opaqueness of these systems is a challenge, and the traditional quality assurance techniques losing the steam. So the question is, can things go wrong? And the answer is yes. If there are small changes to the correctly handled inputs, then that can lead to unexpected or erroneous behaviors. And also there are some type of adversarial attacks. So in 2014, an integrating property was observed that when the left image is fed to a neural network, it is classified as a panda with 57.7% confidence, but when we add a small amount of noise with it and fed it to the same neural network, it gives a classification of gibbon with 99.3% confidence. So the small perturbations of inputs lead to misclassification. A more serious concern is when we just add 11 white pixels with the traffic light image, it is misclassified as a kitchen oven. So what are the challenge? First is ensuring the robustness of these ML models before deploying, and the second is energy efficient neural networks like spiking neural networks used in safety critical systems must be rigorously verified to prevent the unforeseen accidents. So our objective is to bridge the gap between the energy efficient neuromorphic computing and formal robustness guarantees, ensuring the sigma delta neural networks can be deployed with confidence in real world applications, and also to establish a robust framework for formal verification of SDNNs, the most prominent model in the neuromorphic computing. So here is our contributions. We first propose a method to encode the SDNNs as Satisfiability Modulo Theory SMT constants, enabling a comprehensive and expressive representation of SDNN behaviors. Second, we leverage the SMT encodings to perform the rigorous verification and robustness analysis of the SDNNs. And next, we present our experimental results on temporal versions of the benchmark dataset MNIST to demonstrate the validity and correctness of our SMT-based model. So before going to the sigma delta neural network, we just define the verification problem once. So let's suppose this is a SDNN sigma delta neural network, and there is an input space x bar and there is an output space y bar. We first define a property, input property p over the input space, and also we define a output property q over the output space. So defining after this, the verification problem in case of SDNN is as follows. For a SDNN n from x bar to y bar and an input property p of x bar and an output property q of y bar, thus there exists an input x naught bar and output y naught bar such that x naught bar satisfies p and the output y naught bar satisfies the property q, where p of x bar satisfies the So basically that characterizes the input we are checking, and Q of y bar characterizes the undesired behavior for those inputs. And if this problem has a negative answer, that means it is unsat or unsatisfactory. That means the property holds. And if it gives a positive answer, that is satisfactory, that includes a counter example. So now the SDNN, so it is the most prominent model in neuromorphic computing. It is energy efficient like SNNs, but the only difference between SNNs and SDNNs are, instead of using the binary spike, it uses real values. And so SDNNs are a specialized type of neural network that process the changes in activation between consecutive inputs rather than decomputing the entire activation. And it has two key mechanisms. One is temporal difference or delta, and temporal integration or sigma, which focus on detecting and accumulating changes in the input over time. So here is an example. So the first A is the original network, where the traditional weight multiplication and the W1x is the weight multiplication and H1x is the activation functions. Next, we define the temporal difference and temporal integration operation, and we introduce these two in the original network. That will give you the temporal difference network. You can see like here are two algorithms in the bottom, algorithm 1 and algorithm 2, corresponding to the delta and sigma. The delta algorithm just computes the difference between two consecutive inputs and report it, and while doing so it just like rewrites the previous input with the current input, and on the right hand side the sigma operation, it is just accumulating the changes over time. Now in picture C, you can see that is a rounding network where the round operation is introduced before the weight multiplication, and merging this B and C will get the sigma delta neural network where both rounding, sigma and delta operations are included. Now next we define the adversarial robustness problem in SDNNs. So for a classification problem with n classes, we first design SDNN n with the n number of output neurons. Then an SDNN n is trained for classification in adversarially robust when the small perturbation to a given input sequence gamma naught does not lead to a change in the predicted class y naught is equal to the majority voting of eta naught, where eta naught is the output of the SDNN. So now depending on this, we encode a formula, that is P of gamma and n of gamma is equal to eta and naught of Q of eta, but P gamma is the it states that gamma is a perturbation given the input sequence gamma naught, and Q eta states that the majority voting of the output eta should be equal to y naught. So given SDNN's unique event-driven processing and temporal dependencies, traditional verification methods for the dense neural networks may not be directly applicable or in this case. Then we have the SMT, and with its capability to encode the discrete state transitions and sparsity constants, it emerges as a compelling framework for analyzing these SDNNs under adversarial and safety critical conditions. So now we introduce the SMT encoding. So SMT is a very powerful formal verification technique that extends the Boolean satisfiability by incorporating different mathematical theories such as linear real arithmetic. So SMT encoding of a given SDNN involves encoding the execution semantics of the internal and the output neurons. So for doing this, we first introduce some real variables. So xit denotes the values in the input layer for all the neuron ni at time t. Then wij, this denotes the weights between the synapses for the adjacent neurons ni and nj. Then RIT is the output of the round operation, DIT denotes the output of the delta operation, and YIT denotes the output of the sigma operation. So after introducing those real valued variables, we made the constants. The first is the initialization. So initially all the things are initialized to zeros. Then we write down the quantization constant. Then this is for the delta operation. Then the sigma operation, and lastly we have the output constant. So collecting these 5 constants, we define the SMT encoding of denoted as Fn to the given SDNN like this. Next we do a interval bound derivation where we propose a lemma along with the proof that states that for an SDNN, consider consecutive delta and sigma neurons at layers I and the consecutive layer, that is j, equal to I plus 1 respectively. Now let xit and delta it be the input and the output of the delta neuron, and sigma jt is the output of the sigma neuron at time t. Then for all t greater than equal to 1, if we assume that xit is bounded as alpha and beta, then the sigma jt has a lower bound, that is summation over I wij times alpha plus t times bj, and it has an upper bound, that is summation over I wij times beta plus t times bj for all t greater than equal to 1. Then following this lemma, we introduce the bound constants, that is for each neuron we use the SMT to encode these bounds, and we just put this bound, extra bound, with our previously the vanilla SMT, and we get this encoding of the neural network. Now the temporal data processing by SDNNs. So what do you mean by temporal data? So basically it refers to the data that is recorded or observed over time, where the order and time intervals between the observations are important. So unlike static data, which represents a snapshot of at a single point in time, temporal data captures how the values evolve over a sequence of time steps, and it can be processed efficiently using the delta and sigma modules, capturing changes rather than the raw values, making them energy efficient for time dependent applications. So next we introduce the temporal MNIST. So temporal MNIST is a temporal version of the MNIST dataset that is useful for testing models that need sequential data, like in our case SDNN, or in the SNN, that is spiking neural networks. It emphasizes on the spatiotemporal relationships by using the minimum L1 distance to choose the next image in the sequence. So here is the algorithm in small details. The first we create some buckets where each bucket contains images corresponding to specific digits. So there are 10 digits, 0 to 9. So 10 buckets are there based on their labels. Then randomly initialize a buffer of length 1000 by selecting 100 unique images for each digit from the corresponding bucket. It ensures no duplicate images within a bucket are added to the buffer. Then we generate the sequences by repeatedly choosing the images with the minimum L1 distance to the current image. So what we are doing, for each sequence we first randomly select an initial image in the buffer, then replace the current image in the buffer with a new random image from the same labels bucket. Then in the third step we find the closest image in the buffer using the L1 distance and append it to the sequence. And we repeat these 3 steps until the desired sequence length is reached. And now what is the level of each of these sequence? So it is determined by the majority voting of the images labels. So here are some sample images from the temporal MNIST of sequence length 16. You can see. Now the formulation of the adversarial robustness in SDNN. So we use a specific type of definition for the adversarial robustness in our framework. It says that for a given non-negative integers delta, small delta and epsilon, the delta perturbation of a temporal input sequence gamma naught with temporal window t refers to changing it by at most delta frames within t, where each frame can change by at most small delta many values within the frame, where each value can change within a frame by at most plus minus epsilon. So basically we have three hyperparameters, or basically we have three parameters: capital delta, small delta and epsilon. So for example, if delta equal to 7, small delta equal to 400 and epsilon equal to 100, so this is the original sequence from the temporal MNIST. After perturbation, this goes to this, and the perturbations are that in that indices 7, 3, 8, 5, 2, 15 and 11. Now after doing this, we get the end-to-end framework where, so there is a pretend SDNN comes to our framework, and we encode that first. Then also the input property p gamma and other input constants are coming, and the output property is coming. All these things will go into a constant solver, and the constant solver will give you either two outputs. It is either give you a SAT or it will give you an answer. So here are some results of on the temporal MNIST dataset we got. So we run three distinct experiments based on the parameter values, capital delta, small delta and epsilon. The first experiment shows that if there is a complete frame drop, so where one or more frames within the temporal window are removed entirely, and all the values in each of these removed frames are set to 0. So these are the results with different variable sequence length 4, 8, 16 and 32. Interestingly, if you see, like in all the when the temporal window length is small, both the vanilla SMT and the SMT with interval bounds perform like equally, but when the length increases, the SMT with interval bounds have like overtaken the vanilla SMT. The second experiment shows that partial frame drop with complete frame perturbation, where a subset of values within the chosen frame is set to 0 instead of removing the entire frame, evaluating the network's response to partial occlusion. And the third experiment shows that partial frame drop with partial frame perturbation and partial pixel perturbation, where selected pixels within the drop frames are perturbed within a predefined range epsilon, further testing the network's robustness. So more results are in the paper. So in conclusion, we first define a symbolic SMT-based model for adversarial robustness verification of a given SDNN, and we also show that how simple bounds can be derived on the sigma units that can expedite SMT solvers, and we also define the adversarial robustness property motivated by the video stream processing. So here are some related works for our paper. Thank you for your kind attention.
Okay. Thank you for the great talk. We will get only one question. Any questions? Okay, I have one question. Okay, it looks like you used a really small data set like the MNIST, right? So, and can you use the larger data set or not? If not, is there any constraint for constructing the SMT-based model or constructing the large SDNN or something like that?
No, basically, we are currently working on the larger data sets. So this SDNN is used in different architectures. So it is we are currently working on a NVIDIA's architecture that is called PilotNet. So that uses this SDNN architecture and it has a big data set. So we use our framework, integrate with their data set, and there is also the convolution operation is there. So we integrate those things and we will submit like our
Okay, okay. It's just problem of the time. Okay. And how long it will take for the verification?
For this work or
Just this one.
we give a 1 hour like time of period. So all the results are within 1 hour.
Okay. It looks reasonable. Okay. Thank you.